It's now my pleasure to introduce our next speaker, Dan Schrag, who is professor of geology and environmental science and engineering at Harvard, and also director of the Harvard Center for the Environment. Along with Christine Castle, whom you'll hear from tomorrow on our panel, Dan is one of two members on our program who are members of the President's Council on Advisors on Science and Technology, or PCAST. Dan, it's great to have you here. We've been talking about and thinking about climate since we began last evening, and it'll be great to hear your talk. Thanks.
Great. Uh-oh. What's wrong? Okay. Thank you. Thanks to Doug, to Chris, to Jerry, to everyone. I first came to SFI in the summer of 2001, I think it was, to give a public lecture downtown, and I spent a week here. And I loved it so much that I came back the next spring on sabbatical for the spring. And it was just, I overlapped for a month with David Krakauer, who was brand new, just arriving. I had such a good time that I have persisted. I think I spoke at this event in the fall of that year, so 2002. So that was 10 years ago, and I met Michael and others. And I have found SFI to be such a source of stimulation and inspiration over the last decade. So it's been a very important part of my intellectual development. I'm going to talk about resilience today. I'm going to talk about climate change a little bit. Some of you have heard me talk about climate change because I've talked in this group, I don't know, 3 or 4 times over the last decade. And I don't want to just talk about that. I want to actually talk a little bit about resilience, especially in light of Hurricane Sandy. There was earlier discussion of is this hurricane caused by climate change? And we've heard some of the discussion of that. Of course, no individual storm can be attributed to a broad phenomenon like climate change. But this isn't just a hypothetical question for me. During the storm, I was sitting at home in Boston. School was canceled, so I was home with the kids. Harvard canceled classes. And I got a call from a friend in Seattle who's an NPR reporter, and he was going live with some report on the storm and wanted to interview me. And, of course, what is the first question that comes up? Predictable, right? So what do you say? It's actually pretty tricky. Let me just tell you something. First of all, I want to disagree a little bit with Chris earlier. I actually do think it's important to discuss whether or not this is related to climate change, because climate change gives us some sense of whether this is going to be a greater and greater problem in the future, or whether this is just a one-off event that is going to happen every now and then in a stochastic kind of way. I will say, by the way, how many people here from Connecticut? Michael used to be from Connecticut. So a year ago, you forget, just a year ago, we had the ice storm in Connecticut. Hundreds of thousands of people were without power for 3 weeks, and the weather was a lot colder. People died. Several people died in their houses from carbon monoxide poisoning because they were trying to heat their homes with their lawnmowers. That sounds stupid, but I think when you're really cold and you're without power for 2 weeks, you actually begin to do stupid things. And people died. So that was a really bad ice storm a year ago. What I'm going to show you is that we've had a lot of strange weather, but what I want to talk about is ways that this hurricane first might be related to climate change. And there's a lot of work being done as we speak on this, and the jury isn't completely in. But I actually think the way that we were talking about it before is probably the least interesting, and that is the general impact of climate on hurricanes. I think Abbas did a wonderful job talking about natural disasters, and he mentioned Kerry Emanuel's work. Kerry is my colleague at MIT, and he's done wonderful work on hurricanes. And what he's shown is that the total energy dissipation by tropical cyclones in the Atlantic has been strongly correlated with rise in sea surface temperatures. And that makes sense for some very clear physical reasons in terms of how storms get energy. But let me explain that actually isn't necessarily that relevant to this storm. And the reason is that the total energy dissipation integrates across all storms, all different sizes, all different time scales over the hurricane season. And so any one storm really has no relation to that cumulative energy dissipation that's capable of the climate system, okay? And so what you see, this hurricane, it came up from the Caribbean and followed this track here. There was something two things that I think were in particular very strange about this storm. Late October storms are not unheard of. The hurricane season generally goes from, late June to early October. Late October is certainly not unheard of. There have been November and December hurricanes. This was a big hurricane year, although nobody noticed. Remember, Sandy starts with an S. So you had a lot of storms this year, but they didn't hit land. What was different about Sandy was that it actually, first of all, it made this left turn and came right in. Normally, a storm like this, we would expect to kind of swing out to sea like that. That's the way most storms historically have done it. In fact, statistically, prior to about 2007, only about 6% of storms have taken a left turn like this. It's a very unusual track. Okay? In the last 5 years, about 35% of storms have done this. People are working right now on exactly why this is, but there's something interesting going on here that has to do with the reason it turned left here, which has to do with a trough associated with a meandering of the jet stream that some people think is associated with a declining sea ice. And I'll talk about the sea ice disappearance, but there may be actually a connection between the sea ice distribution up in the Arctic, the pattern of the jet stream coming over North America, and how it steers storms. And if, and again, this is a big if right now, but this is just a hypothesis, but if storms start to get more frequent in terms of turning left and coming across the U.S., that is far bigger than any kind of mild change in intensity of the storm, because this wasn't that big a storm. It was that it turned left and made a direct hit on New Jersey that was such a problem. The second thing that was kind of weird was that this was only about 75-mile-an-hour winds when it was up around the Carolinas. It wasn't that big a deal out on Cape Hatteras and out on the Barrier Islands and on the Carolinas. It strengthened between North Carolina and New Jersey. It grew to about 90 miles an hour. Here is one reason why it grew. This is sea surface temperature distribution, if you can see, for last week. And this is just the anomaly. So this is measured as degrees Celsius relative to the average, which I believe, it doesn't say here, the average is probably calculated between 1955 and 1995, but plus, I forget the exact range. In any case, what you can see here is that the temperatures in this region off the coast between the Carolinas and Massachusetts were 3 to 4 degrees above normal. That's a lot. That's a very big anomaly. Now, that is not completely due to climate change. That's partly due to interannual variability, but it is contributed to by climate change. Overall, the ocean is warming, and the pattern of variability is changing as well, and this clearly had something to do with why this storm strengthened instead of weakening. Normally, a late October storm would hit cold water and die out much more quickly. Okay, so there are two examples of ways, not the simple broad brush, the ocean's getting warmer and so there are going to be more hurricanes or bigger hurricanes or something vague like that. Two specific mechanisms that people are looking at. And I think the most important way as we go forward of tying a broad global phenomenon like increased greenhouse radiative forcing of climate to specific storm events is going to be to think about mechanisms. I'll talk about this with heat waves as well. So it wasn't just a weird year for storms. This was a very strange weather year in the U.S. It was a very warm winter. Anybody here from Michigan or Minnesota? Okay, you remember March? This is what the U.S. looked like in the middle of March. This was probably the most incredible weather event we've ever experienced, and everybody thought it was wonderful. Right? It was actually really bad if you're an ecologist and you care about maple sap and maple syrup, or if you care about apple harvests weren't very good this year, partly for this reason. But not only did we have a mild winter, but this was the return of summer in the middle of March. You can see here this pattern of temperature anomalies, 25 degrees Fahrenheit above normal in this part of the country. It was amazing. It lasted about 2.5 weeks. When I say amazing, I mean meteorologists, we were all scratching our heads. We couldn't believe what was going on. In Rochester, Minnesota, the overnight low temperature broke the record for the all-time high. That doesn't happen. When we break temperature records, we break them by a degree. We were breaking temperature records in Michigan and Grand Rapids by 30 degrees Fahrenheit. That's weird. Honestly, meteorologists don't know what to say about that because it's so completely far out on the tails of what we expect. Chicago, 80 degrees Fahrenheit for 8 times in 9 days. If you had said in February, what's the probability of getting one 80-degree day in Chicago in mid-March, you would have looked at the historical record and you would have said 0. Almost 0, because the record was like, I forget, 70 or 69 or something like that. It just wasn't, it just was so far out on the tails. This is, if you calculate it using normal statistics, the data are not normally distributed, but if you calculate it using normal statistics, this would be like a 6 or 7 sigma event. Okay? This is a very unusual event. St. John, New Brunswick, I love this one. The temperature on March 22nd broke the record for any temperature ever measured in April. Okay, this was really weird. This wasn't the only weird weather we've had. We had another sort of 6 or 7 sigma event in 2010 in the summer. I don't know if anybody was in Moscow that summer. In Moscow in 2010, this is July, showing this period of anomalous warmth. If people remember the summer of 2003 in Europe, I was in Italy that summer. It was amazingly hot. 15,000 people died in France from the heat wave that summer. 15,000 people. The harvests in Europe were about 30% down from their average. And that was a big year. That was about a 3.5 degree anomaly or a 3 degree anomaly. On a summer average, this would be closer to a 5 degree anomaly. But you see, in this region, it was 8 degrees warmer than average for this time period of July. Forest fires all around Moscow. Huge smoke inhalation problems in Moscow. This was a really big deal. Here is the distribution of summer. This is now summer average temperatures. So you'll see this is closer to a 5 degree anomaly. So this is all of the data for the last 100 years. I don't know why we didn't include 2007 through 2009, but it doesn't show anything different. They fall in this range. But you see here, this is the distribution. This is 2003, that anomalous heat wave in France. And then this is 2010. Really far out on the tails of the distribution. And if you look at this on monthly data, it looks even more extreme. When you average it over the summer, it smooths it out a little bit. If you run a model and you say, and again, the models, I don't hold much with climate models, but they're useful tools for giving a sense of what we know about the system. And you look at what they predict for temperatures by mid-century or temperatures by the end of the century. This is by the last 2 decades of the century. You see that in 2010, that heat wave would be kind of the average summer out then. This is a really big problem. There are lots of interesting issues to watch. 2 that I think may not be quite as much on people's radar as they should be, that I want to just mention in terms of climate physics. One thing that isn't getting talked enough about, but is very, very important in creating these heat waves, is soil moisture. Soil moisture is an oft neglected thing. We don't measure it very well, except we measure it in farms sometimes, but we don't have very broad observational systems set up to measure soil moisture. Soil moisture is a critical variable for the climate, and the reason is, as the land heats up, what happens is, both directly and through plants, through evapotranspiration, water evaporates, and that cools the surface. It's very, very effective. In fact, that's really why plants use so much water. They're essentially air conditioners. They evapotranspirate so they can keep cool. If you were dark green in a hot, sunny day, you would be evaporating a lot of water too. And so what's been happening, we think, is that soil moisture has been declining because of drying out, possibly associated with changes in snowpack in mountain regions. But we've seen, for example, this summer, I was up in Colorado earlier this summer, and it was incredible how little snow there was. That has a feedback that ultimately creates drier conditions. And so when the heat wave comes, instead of having this negative feedback that keeps it cooler, you get an amplification and you end up with a huge heat wave. For example, this summer we had in the middle of July in Kansas, it was 115 degrees Fahrenheit. It was so hot that farmers couldn't go out in the fields because their equipment was too hot to touch. It was really tough. The other is, of course, the decline in sea ice. This year set a new record. So here is the average sea ice distribution that we've measured from 79 through this year. And this is the distribution in mid-September of this year. This shattered the old record, which was 2007, by about 15 to 20% decline. But, you know, two big things have happened. In 2007, that was the first year that the Northwest Passage became ice-free. The Northwest Passage, for those of you who like history, know that it took Amundsen 3 years to get through, an epic voyage. He spent 3 winters struggling to survive up in the Canadian Arctic, and he finally made it through. He spent several years trying to find a way around Russia, and he never could do it, because that was called the fabled Northeast Passage. That was never open until 2010, and if you look at it this year, it's not open. This is wide open. This is changing commerce in the Arctic in the summertime. And now we think it's quite possible in 2 or 3 decades we will see an ice-free Arctic in the summer. Now, directly, the good news is this doesn't affect sea level, because sea ice is thin and it's already floating and displacing water. But what it does do is it actually insulates the ocean from the atmosphere. So it actually keeps the heat that's stored in the ocean seasonally from interacting with the atmosphere. And that plays a very important role. It also affects the jet stream. It affects the weather circulation and the pressure fronts that ultimately determine mid-latitude weather patterns. And so it may be causing some of the unusual weather that we've been experiencing by causing large meandering of the jet stream. That's something that's still being worked on. The other thing it does is it keeps Greenland cold. And Greenland does matter to sea level. Greenland has about 7 meters of sea level equivalent stored on it, meaning if Greenland melted entirely, it would actually raise sea level 7 meters on average. Something very interesting, it wouldn't be uniform. A lot of people don't realize that there's so much ice on Greenland that the gravitational effect of the ice sheet is such that if you lost 1 meter of ice on Greenland, globally average, sea level would rise 1 meter. But right around Greenland, sea level would fall 19 meters. 19 meters because of the loss of mass from the ice and the reduced gravitational field. That's how massive that ice sheet really is. So we also saw something incredible, and this may be the year's most incredible climate observation. So we have been slowly experiencing a rise in the area of melt in Greenland. So here's 96, and what happens is the perimeter of Greenland melts. Greenland is like a big dome. The ice sheet is very high at the middle. The summit of Greenland is about 3,000 meters high. There's about 1,000 meters of ice below sea level because it presses down the continent. And what you see is melting around the perimeter, and then it snows on the top. And the net contribution to sea level, which is about a little less than a millimeter a year, is the result of the summation of those two parts, the addition of snow and minus the loss of ice from around the perimeter. And so you see that the area of melting has been growing steadily, but nobody had ever seen anything like this. So this was July 8th of this year, 2012, showing where melt was occurring on Greenland. And this is July 12th. You see the entire surface of Greenland was melting. Now, the good news is this only happened for 4 days. We are still processing this, meaning glaciologists are still trying to figure out what this means, what this implies for the future. The answer is we don't know yet. There's a lot of uncertainty. But the previous record had been something like 50% area of Greenland melting at any one time. And this summer, every part of Greenland, 97% of the Greenland ice sheet was melting simultaneously. Melt pools change the color of the surface. They absorb more solar radiation because they're darker, so it's a positive feedback. And again, I think this just emphasizes how much we don't understand this system. You know, last night, Michael was saying that there's a lot of uncertainty in this, and it can cut both ways. And that's true. But frankly, I actually tend to think that the uncertainty tends to cut the wrong way, meaning most of the things we don't know are likely to hurt us. And here's a nice example. Of course, we also had a big drought this summer. This is Illinois, extreme heat and drought conditions. People were mowing their corn harvests under. It was a very serious year for corn and soybean farmers. There is very good empirical data. Here is data from corn showing yield as a function of temperature, and it's very clear that above some threshold around 29 Celsius, you get this sort of drop-off in yield. We've seen it in Europe in 2003. We saw it in Russia in 2010. We saw it in the U.S. this year. So temperature by itself, even separate from the drought, is actually a very important thing for crop yields, especially during certain times of the plant's lifetime. And there's a race going on right now in biotechnology by big companies like Monsanto to figure out whether they can develop crops that can withstand higher temperatures. It turns out this is a really difficult challenge because this is asking bioengineering to do something really that natural selection has tried to do for a very long time. There are very hot places in the world, and plants would like to live there, and they don't. And so this is a case where, most of the bioengineering of crops has been reallocating energy from one part of the plant to the other. But it hasn't been doing something like increase in absolute photosynthetic rate or something that evolution has actually worked on very hard. And so this is going to be a very interesting challenge. So we had this big drought, food at risk. We had a doubling of corn prices. Corn was $9 a bushel. This creates problems and will continue to create problems all through the next year. Meat prices will probably continue to go up. And for many Americans, that's probably a good thing if we eat a little less meat. Chris Castle can talk about that a little bit. But I think actually, unfortunately, for many poor people in the U.S., what this higher food prices mean is that their quality of their diet is likely to go down. And that will add to problems associated with diabetes and other food-related diseases. Interestingly enough, from the Financial Times, U.S. farmers eye record profits. $122 billion in 2012, a record. And that was really for two reasons. One was the market response. So the farmers who did okay in parts of the country that either had irrigation or didn't have quite as extreme a drought, they were making money hand over fist, whatever the term is. They were making money like crazy because it was $9 a bushel. So they were getting a lot of money. And then the farmers who lost everything were covered by our federal crop insurance program. And people have now begun to say, well, maybe we actually have too much crop insurance. The farmers have no incentive to adapt to this kind of calamity or prepare for it. They can be as risky as they want because they know the feds will bail them out if there's a problem. So that's a really interesting issue. Okay, and I'm not going to talk about climate change any more than I already have now, except to say, conclude a few take-home lessons. CO2 is still going up. It's almost 400 parts per million. It probably won't get there next year. It'll probably be there the year after. This is a really big deal. The pre-industrial level was 280 parts per million, and we are going to be at 500 parts per million by mid-century. This is geologically a very big deal. But one of the things that people often aren't aware of is what happens to that CO2. It turns out that only half of the CO2 we put in the air actually stays there after a year. And that's good news. The land, the trees actually take up about a quarter of it, and the ocean takes up another quarter of it. The oceans, the land is limited by how fast plants can grow, how fast the trees can grow. The ocean is limited by mixing. You have to mix the carbon. It dissolves in seawater and has to mix into the deep ocean. And that's limited by things like the winds and the rotation of the earth and the tides, and those are hard to change. So if we stopped putting in CO2, immediately, this is just a cartoon showing roughly what would happen over the next few thousand years. So immediately, something like half or 60% of it stays in the atmosphere. But then it would drop. And over the next several thousand years, maybe a quarter of it would still be left, or half of what's there today. And then a little bit more would get taken up by chemical reactions with calcium carbonate shells on the ocean floor. But there's this last 10 to 20%, this long, flat part that says it's only taken up by reaction with igneous rocks. This is a natural process we call chemical weathering, but it's very slow. So the Earth will heal itself. The Earth will be fine. But it will take about 100,000 years to remove the last 10 to 20%. Or to put it another way, a third of the CO2 that's in the air now from human activities, a third of what's left in the air will still be there 20,000 years from now. So this time scale of climate change is much longer than people think. If you compare that with nuclear waste, high-level radioactive waste 1,000 years from now is about 1,000 times less radioactive. Whereas for carbon dioxide, 1,000 years from now, roughly 30% of what it is today. So it doesn't dissipate the way radioactive waste does. It has a much longer time scale. So let me just make these quick points, and then we'll move on to talking about resilience and how we think about that. Climate change will bring surprises. Calculating, for example, I often hear economists say, here's what using our models, what the economic impact of climate change is going to be. That is, I think, a perfectly worthy exercise, but one that you should realize is fundamentally hopeless, because there will be surprises. We're doing an experiment on the planet that hasn't been done for millions of years, and no scientist understands the impacts or the way the feedbacks work well enough to predict exactly what's going to happen. The second point is something that a lot of climate policy people don't understand, and this one is a little bit depressing, but I think is one of the reasons why this is such a difficult issue to work at both the national and international scale, and heard somebody mentioned it at the local scale as well. What the climate system cares about is cumulative emissions over a time scale of about a century. It is remarkably insensitive to the emissions trajectory. So you could have an emissions trajectory like this or like this, but if the integral over the century was about the same, what the climate system cares about is the total amount of release. What that means is that near-term goals are not a very good metric of success. It's about getting to zero. Okay? It also means that reducing emissions over the next few decades really don't have much effect over what the climate experience is going to be. And this is why it's so difficult for social action. This isn't just the problem of getting China and India and Europe and everybody else on board. Actually, to me, that's sort of the least problematic. Yes, it's a grand collective action problem, but the truth is, if the US and China were really worried about this and were serious about it, my guess is we could get the rest of the countries in the world to go along. I think the much bigger problem is what we're asking society to do today is to make major investments in energy infrastructure for a benefit that really is not going to affect them substantially over the next several decades. We don't often, climate advocates don't like to say it that way for obvious reasons, but it's true. And that's one of the reasons this is politically so difficult. The goal is zero emissions. We care about getting to zero, or very close to zero. So what the target is for 2020 or 2030 is sort of irrelevant. We need to put incentives in place to get the market to work, to make investments in innovation, to get new energy technologies to solve the problem. But again, annual emissions reduction, whether we get to a 20% reduction by 2020 or a 15%, the climate system actually doesn't care that much. The climate system cares about cumulative emissions. And, of course, the climate timescale is long, and the timescale of mitigation is at least decades to a century. So that's the way I think about it, that we're performing an experiment at a planetary scale that hasn't been done for millions of years, and our best models tell us there will be winners and losers, but that many impacts are going to be severe. And we can talk about all the different impacts. I'm not going to go into any more of them, except maybe I might mention sea level a little more. Droughts, heat waves, floods, storms, sea level rise, mountain snowmelt. We could talk about all of them. Mountain snowmelt is a really big deal. We use mountain snowpack as our reservoir, and that is a predictable consequence of climate change, that mountains will not store snow the way they do today. And that means we're going to have to figure out how to store water if we expect we want to use it in the summertime, because those rivers are not going to be flowing throughout the year the way they do now. But they're going to be surprises. Okay? So when we think about these sort of impacts, that's where the discussion of adaptation and mitigation comes in. And I think we've been using the word resilience, and Jen really nicely defined resilience from an ecological perspective, and later on I want to come back to that definition. But first I want to make it clear what the climate community means when they talk about mitigation versus adaptation, because sometimes those words are used in funny ways as well. Mitigation technically could mean mitigating the impacts. That's not how it's used. Mitigation refers to stopping the root cause of the problem, the greenhouse gas emissions. Whereas adaptation is figuring out how to respond to climate change to reduce the severity of impacts. our colleague John Holdren, who's President Obama's science advisor, has a great line about this. He says there's only three things you can do about climate change. You can mitigate it, you can adapt to it, and you can suffer. And we're likely to do some of all three. I think the only misnomer in there is it makes it sound like mitigation and adaptation are options that are somehow trade-offs. And that may be true in the political realm. It's not true ultimately in terms of the cause, and that's what I want to make very clear. Substantial climate change is unavoidable. We already have enough carbon dioxide in the air that we're experiencing substantial climate change, and there's a lot of inertia in the system built in. We will get to 500 parts per million. I think it's very likely we will get to 600 parts per million. If you look at various scenarios of energy technology transformation, that's the best we're going to do. The question is, do we go to 800, 1,200, 1,500 parts per million? That's really what matters. Therefore, adaptation is essential. It's not really an option. We're already adapting to climate change, but it's not going to be cheap. Here's the Thames Barrier in London, often referred to as a nice example of adaptation. And this, of course, is due to subsidence, but the Netherlands really understands about dealing with sea level because a lot of their country is underwater. And they're worried about climate change because climate change and sea level rise only makes the problem worse. They, of course, invest in very serious infrastructure to deal with it. Their engineering is among the world's best, as opposed to what the U.S. Army Corps of Engineers did in New Orleans. This is just after Hurricane Katrina. So honestly, this would be funny if it weren't actually true. There were 400,000 people in New Orleans, in the metropolitan area of New Orleans, when the hurricane came ashore in Mississippi. People forget, Hurricane Katrina missed New Orleans. New Orleans flooded over 2 days. If the storm had hit New Orleans, remember, the levees were only 12 feet. The storm surge in New York last week was higher than the storm surge from Katrina in New Orleans. If Katrina, as a Category 4 storm when it came ashore, had hit New Orleans directly, that people thought it was going to be an 18 to 20-foot storm surge, that city would have flooded in 10 minutes, and you would have lost 100,000 people. As a result, only 3,000 people died in Katrina. We averted a major disaster there. It was an expensive one, but the point is, this isn't because the Army Corps of Engineers are terrible engineers. This is because we weren't willing to make the economic investment. And I want to come back to this because in the U.S., Abbas talked about the World Bank and about poor countries in the world making large infrastructure investments. The U.S., ironically, is less likely to make large infrastructure investments for climate change, I predict. I just think that they're very unlikely, and I'll explain why that is. Let's briefly talk about sea level, just as an example of how complicated these issues are. Here is all the different factors that could influence sea level. So you have terrestrial storage of water, ocean circulation, changes in the ocean and atmosphere, melting of ice, and then, of course, vertical land motion. Vertical land motion, people forget, but continents are moving up and down. So here are sea level records from 1900 to 2000 from different places in the U.S. You can see that some places sea level's gone up a lot, or some places sea level's actually dropped. Why is that? Well, Sitka, Alaska's been uplifting, whereas Galveston has been subsiding. All that oil getting withdrawn from the Gulf. Okay, so you see different sea level patterns. Not surprising. So it's actually complicated, and people who study sea level have to correct for all of these things. So these are observed global mean sea level from tide gauges from all over the world between 1900 and 2001. And what you see here are sort of an initial rate of something like 0.5 millimeter a year, and then this rate of about 2.3 millimeters a year. Although that's a line drawn through all of the data, there's this sort of recent part that looks like it may show an acceleration. We actually have new observations now, 2 decades of satellite altimetry. These are satellite measurements of the sea surface, the Topex-Poseidon data. And it basically measures the two-way travel time of the reflection and gives global data from the satellite that's passing over all the places of the Earth fairly frequently. And that's what the data look like from Topex-Poseidon. It's much better data for studying sea level. And there's lots of information in the spatial variation as well. But if you take the global average, this is what you get from the Topex-Poseidon, and it's an estimate of about 3.4 millimeters a year. So it seems like there's been an acceleration. There's a very important point here, which is, so So we have 3.4 as opposed to the tide gauges, which show 2.3, but maybe this is the 3.4 part right here. It looks like it may be accelerating. The point is, about 3 millimeters a year, that's already at the upper end of what the IPCC projected. This was what the IPCC projected for sea level, and this is just an example of how conservative scientists really are. They projected something like 20 to 60 centimeters over the century. But with so much uncertainty in things like ice sheet melting, and they basically just held all those things constant. So they just assumed that Greenland would keep melting at the modern rate without change. So for Greenland, for example, we have satellite measurements of the gravitational field. This shows that Greenland's been losing mass at about 250 cubic kilometers of ice a year, which sounds like a lot, but that's only half a millimeter of sea level rise a year. So 5 centimeters over the century. So when the IPCC projected sea level rise by 2100, they assumed 5 centimeters. That is, Greenland isn't going to accelerate even as the Earth warms. There's this built-in conservatism to scientists. We believe in 95% confidence intervals. This is actually a big problem because there are a lot of things that are highly uncertain but highly impactful. So let me give you another example of this. This is the Ross Ice Shelf. The Ross Ice Shelf is a massive piece of ice. It's about 1,000 meters thick, covers most of the Ross Sea here in Antarctica, and essentially it acts like the buttresses of a cathedral. It keeps the ice from East and West Antarctica from flowing into the Ross Sea. If the Ross Ice Sea were to break off and float off as a giant iceberg, as some have done on the Larsen Ice Shelf and the Pine Island Glacier out here on the Antarctic Peninsula, if the Ross Ice Shelf were to break off, glaciologists estimate that massive quantities of ice would quickly flow into the Ross Sea from East and West Antarctica. And you could see 1 meter or 2 of additional sea level in a century. Okay? But the truth is, we have no idea. In fact, we know how this would happen. What would happen is it would actually come not from surface warming, but because of warming from the ocean from below. But here's the problem. The only measurements we have from the perimeter of Antarctica actually come from thermometers strapped to seals. Seriously. That sounds sad, but it's actually true. Our observing system is so lousy that we have no idea whether this is going to happen, is already happening. We have no idea. We don't have the observation network put in place. And so when people sometimes in the literature talk about this as a high consequence, low probability event, and the only reason they refer to it as a low probability event is that it seems kind of extreme because it's never happened before. Right? But in fact, it could be 100% probability. It could be happening now. It's just uncertain. It's just unknown probability. There's no way to attach a probability to that happening because we don't have any observations of the perimeter of Antarctica. What matters is warm water, and when I say warm, I mean 2-degree water, 1-degree water, instead of the -2-degree water that's there now. So it's a very subtle change in intermediate water on the perimeter of the Antarctic shelf, and that we don't know whether it's happening or not. Okay. But with all that ice, by the way, Greenland's 7 meters, Antarctica is like 60 meters of sea level equivalent. The point is that without mitigation, effective adaptation becomes nearly impossible. It isn't a choice between one or the other. You really have to do both. And I think that's important. But let's talk about the adaptation side, because often the adaptation side doesn't receive enough attention. And interestingly enough, this should be the part that is most easy politically, because it's the one that actually has an impact on our lives. It might actually help you out next year. Right? So let's talk about resilience. Jen, I apologize. I put in other definitions of resilience to look at. Where's Jen? Is she in the back? And I looked at Holling's definitions too, but I thought that you would show them, and you did. So that's great. If you just go to the dictionary and say, how does this term popularly used? Here's the definition: the capability of a strained body to recover its size and shape after deformation caused especially by compressive stress. An ability to recover from or adjust easily to misfortune or change. So from Wikipedia, though, it gives a slightly more ambiguous definition. In ecology, resilience is the capacity of an ecosystem to respond to a perturbation or disturbance by resisting damage and recovering quickly. Well, what we saw is actually, I think the more technical definition is recovering quickly as opposed to resisting damage. The resisting damage would be something that we might call robustness, and Doug mentioned this earlier. Right? Robustness, the ability of a system to resist change without adapting its initial stable configuration. So the way I like to think about it is the Terminator, he's robust. But Terminator 2, T-1000, he's resilient. Right? If people remember the second Terminator movie, this is the liquid metal guy who's really freaky, who, bullets deform him, put holes through him, shatter him apart, and he reassembles and is good as new in a few seconds. Right? He's resilient. Arnold Schwarzenegger is robust. And for anybody who knows, it's the resilient guy who mostly wins until the very end. So I think that's a nice way to think about it. So in terms of building resilience relative to all of these, obviously, it's pretty specific. When we talk about resilience to floods or to storm damage or to sea level rise, that's obviously different than to droughts or to crop failure. And so there are going to be different types of resilience that we're going to have to build in. If markets function well, crop failure may not be such a big problem, provided that our food distribution systems and markets work effectively and we get the incentives right so that the farmers have the signals to plant the right crops that are not taking too big risks. And of course, we have to figure out maybe ways to think about modulating the impact of high food price spikes on poor people who get in trouble when suddenly food prices double over the course of a month. I'm going to talk briefly about something specific about climate change resilience relative to Boston. And the reason is, last semester I taught a course with 2 law school professors and 2 design school professors on sea level rise and cities, specifically focusing on Boston. It was a very interesting experience for me, and it changed the way I think about investments in climate change adaptation altogether. For those of you who don't know, Boston is probably the easiest city in the U.S. to protect, coastal city, to protect from damage from sea level rise. And the reason is, most of Boston is focused around the Charles River Basin. And the Charles River Basin has a relatively narrow outlet protected by the Charles River Dam right here. That's the Museum of Science. And the Charles River Dam essentially keeps the level of the Charles steady. So during high tide, it keeps the ocean out, and during low tide, it keeps the water in the Charles in. The Charles used to be a tidal river, so it has a rich history. Here's the history of the Boston area back from, you can't really read this. This is 1830, 1850, 1890, 1916, 1934, 1995. So you can see that the evolution of the whole Charles River Basin and the Boston area, the geography has changed enormously over the last 150 years. Except right now we're quite invested in the way it looks today. When Harvard was going to build its new campus across the river in Allston, there was a serious suggestion on the table to just move the Charles River. The big problem was crossing the Charles, so let's just move the Charles River on the other side of the business school and connect all of Harvard campus. And it had been done before. It didn't actually come forward as the most prominent choice, but it was discussed. And that's because we have a lot of investment currently in the current configuration. People don't want to move. A graduate student working with me and the design school professors as well looked at a variety of major infrastructure and some soft infrastructure investments in protecting Boston from sea level rise. So here is the current Charles River Dam. 78 was built. The 1978 nor'easter came within 16 inches of topping the dam, just so you know. So if you look at the sort of highest storm surge we've ever seen, which was that 78 event, we have 16 inches of protection. And if you think about 16 inches over the next 50 years of sea level rise, you begin to say, oh my goodness, well, we'll probably have to raise the height of that dam. But if you do, it turns out there's other places for the water to spill around. And so immediately you're drawn to other places. You might want to build a dam here. Or you might want to protect the entire Boston Harbor region. Here's the airport, or here's the airport. You want to build some complicated structure that would include gates that would let ships in during low tide. I mean, this would be a really complicated structure. It's something that the Dutch have built. I mean, so it's not unheard of to build this. It's just very expensive. This would be a $10 to $20 billion investment. This would be like another big dig times 2. So let me just give you some thoughts on resilience and robustness, because I've got to say, I found this morning's talk really inspiring and very important to think about the types of investments and this emphasis on different types of investments in different places. Many places around the world are struggling with this. People forget this past winter in Bangkok, they had historical flooding. People had to essentially evacuate the entire city of Bangkok for weeks. It was incredible. They've done a remarkable job of recovering. So here are some thoughts on resilience and robustness with respect to climate change. One of the lessons I learned from this course is that at least in the U.S., and I want to talk a little bit about the U.S. now, only because we heard about more the international side this morning, and I think there are different challenges, political and economic challenges, in the U.S. than there are overseas. First of all, I think we need to distinguish investments in robustness from investments in resilience. So seawalls versus pumps and waterproof systems. I've been saying this a lot, actually, and I wish I hadn't had reason to say it more. After Irene, which almost flooded the subway system in New York, I used to give talks saying, maybe instead of building a seawall in lower Manhattan, the problem is you build a seawall, the storm surge in Irene was 9 feet, so you build a 12-foot storm seawall, and then along comes Hurricane Sandy at 13 feet of storm surge, right? That's the problem. How do you prepare, especially when sea level is going to continue to rise? So instead of investing in the seawall, maybe what you have to do is make New York City more resilient. Let the subway system flood, but make sure that the pumps are there, and the plumbing system is there, and the electrical wires are coated and waterproof, so that, yes, you might have a $50 million disaster, but it's not a $10 billion disaster. And I think, honestly, that's, if we look at the economics of these investments, that's going to be a very important strategy, which is to say, you know what, in less urban areas, instead of saying keep your house from flooding, you say, you know what, your house may flood, but make sure everybody has a sump pump in the basement. Make sure that everybody has the right design such that you don't have to condemn all of the buildings after they're flooded because they're full of mold and their foundations are destroyed. So how can you design buildings to make sure that they can withstand a big flood and be pumped out and still be okay? And the same goes for other infrastructure like sewage treatment plants and electrical systems and everything. I think we have to distinguish between hard and soft investments, wetlands versus seawalls. And also, I would say that most effective policy measures are likely to align with economic incentives with individual and societal decisions to put people in harm's way. We still have a lot of perverse policies in this country. The biggest one, I would say, is federal flood insurance. My brother-in-law and sister own a place on Fire Island. It's in the middle of Fire Island, and I think it's still okay, luckily. But they almost bought, about 10 years ago, a house right on the edge, right on the ocean. In fact, it was one row of houses ahead of all the other houses on Fire Island on the ocean side with a panoramic sort of 270-degree view of the ocean. It was the most incredible house. It was there because all the other houses that were next to it had all washed into the ocean. And they looked at it, and it was for sale for $1 million. It was $1 million, and it was clearly a $2 million house. But it was $1 million because you could get no flood insurance for it. So you had to basically pay cash for it, and you could get $400,000 from the federal government for insurance. Now, my sister didn't buy the house. The house was still there. I don't know if it's still there now, but it was still there as of before Sandy. So it's an interesting question of risk and how people tolerate risk. But here's the interesting thing. Why are taxpayers subsidizing $400,000 of federal flood insurance for a house like that? That's just crazy, right? And that's true for the Outer Banks in the Carolinas, and that's true for Cape Cod. My house on Cape Cod, recently the insurance industry threatened to walk away from all housing on Cape Cod because the insurance was too low priced. And the state negotiated. They basically said, if you withdraw from Cape Cod, you have to withdraw from all of Massachusetts. We won't let you sell insurance at all in Massachusetts. So they made a compromise, and they basically created a high-risk pool. So my insurance prices went up about 50%, and now people in Worcester and in western Massachusetts subsidize my insurance on Cape Cod. It's great for me, but it's crazy. So one of the things we have to think about, I think, is deregulating insurance. So approaches for the U.S., not necessarily relevant for the rest of the world. I think the most important policy levers for increasing resilience to climate-related impacts are at the state and local levels. And that's one of the things I learned from this course. It's building codes, right? It's zoning laws. And the federal government has almost no control, and in most states, the state has ceded control of this to municipalities. And that means it's really difficult to change at large scale because every municipality has its own interesting politics. Second, I think deregulation of the insurance industry and reform of programs like federal flood insurance and crop insurance are an incredibly important way of moving forward on this to encourage responsible investments in robustness and resilience. And I think the idea, what Columbia, you said about that Columbia was working on ways of including this in mortgages. I think that's exactly aligned with what I've been thinking about recommending to President Obama in terms of thinking about risk in housing markets and getting Fannie and Freddie to begin to price some of these in their mortgage valuations. Because frankly, it directly relates to the recovery of their investment. My own view is that U.S. is unlikely to support large infrastructure investments. The seawall in southern New York, southern Manhattan may be an exception. The cost of that seawall, of that dike in Boston, is probably $20 billion. The state of Massachusetts can't afford it, and more likely, politically, there is no way the rest of the state of Massachusetts is going to pay to protect Boston Harbor. Politically, that's just not going to happen. I think it's a very different situation in other countries which are much more nationalized, where federal governments are much more in control, and there's often one or two cities that are more important. So protecting London in the UK, I don't think there's any city in the US that has that same role. I don't think we would protect Washington, D.C. that way. Seriously. It's nice to think, but I actually think we're not going to spend $20 billion of taxpayer money. If you look at the Big Dig in Boston, which is kind of, I think, put an end to all of these sorts of projects, the Big Dig was the result of decades of Tip O'Neill's political victories and would not have happened without his leadership, I think, of the House for many years. And I think we're unlikely to see another Big Dig again. Now, I'm not saying that large infrastructure projects wouldn't be a good thing in many places. I'm just saying it's very difficult to do right now in the U.S. politically. And so I actually think that controlled migration, soft robustness, and resilience, they're most likely to receive the necessary political support. And so they're actually going to be more and more important. So taking all of this, I want to step back from this and actually relate this to some of the things we heard this morning from Jen Dunn, because I've been coming to Santa Fe now for 10 years, listening to ecologists and biologists and physicists talking about robustness and resilience. And I actually think there may be really an interesting opportunity to really engage whether there are some fundamental lessons here where we can take the lessons from ecological work on robustness and resilience and improve our approaches to climate change adaptation. Are there approaches that biology has developed through natural selection that could inspire engineering and organizational approaches to dealing with different types of climate-related risk? Now, in engineering, in bioengineering, a hot field is biologically inspired engineering. That is, not bioengineering. You're not even necessarily working with biological materials, and you're not perfectly mimicking. It's not biomimicry. It's not mimicking biology, but it's taking some of the principles and approaches from biology and applying them to physical systems, perhaps using different materials and different applications. And I think the same general idea works, borrowing from biology to begin to think about how do we design networks, whether it's electricity networks. By the way, right now people in the East are suffering because after several days, close to a week now, without electricity, it becomes really unpleasant. And we've heard today in the news people getting really angry. Having some degree of distributed electricity networks actually would be an incredibly interesting investment in resilience. It might be a little bit more expensive, but that expense at a time like this might actually be well worth it. Even if you could only for 4 hours a day generate some electricity from solar panels on your roof, you could recharge your cell phone, you could recharge your computer, you could do a variety of things. You could run your pump and pump some water into a storage basin. There are all sorts of things that would make life easier if you had a couple hours of electricity today. And I think that's important. And then, of course, the organization of relief and reconstruction efforts as well. A final thing I want to mention before I stop is the question of climate change and conservation. This is something that I think is really interesting. And like Doug, I actually work on the history of climate and the evolution of life over geologic time. I'm particularly interested in a time period around between 700 and about 500 million years ago, which went from essentially small single-celled organisms to multicellular large animals. And there were a number of interesting climatic events over that time, some big glaciations that we call snowball Earths, and then we think changes in atmospheric oxygen as well that may have allowed life to get large, which is very interesting. But when one thinks about biodiversity in climate, I've actually begun to think a little bit about this timescale issue. Because what's been nagging me is that we know that humans don't care that much about the distant future. They care a little bit more than some economists think we do. That is, neoclassical economics uses an exponential discount rate, so anything 100 years out is pretty much worth zero. Now, there's a whole set of work. In fact, Doan Farmer did a nice paper with Giannakopoulos about thinking about other ways of thinking about discounting and how you value the future, hyperbolic discounting, and a variety of other ideas. But what's interesting is that if you actually care about conservation, then you're not talking about a discount rate. And what I mean is, if you really care about conservation of biodiversity, if that is a value, and I know not everybody has that value, but for those of you who do care about conservation, you're not trying to save species so they go extinct 100 years from now, or 200 years from now, or 500 years from now. You don't mind if they go extinct 1 million years from now over natural timescales of extinctions and innovation, but you would rather we didn't have a mass extinction going on right now. And if that's true, then the climate problem looks a little bit different, because suddenly, we have a lot of uncertainty trying to figure out exactly what's going to happen in 50 years or 100 years. But ironically, if you actually zoom out and you look over 500 years or 1,000 years or several thousand years, actually things become more certain. Not the exact number, but suddenly you can say some things with pretty high certainty. I can tell you, for example, 5,000 years from now, all the low-lying tropical islands that have a lot of biodiversity that a lot of ecologists love to study, they're all underwater. I can't tell you whether they'll go underwater 200 years from now or 500 years from now, but I can tell you that in a few thousand years from now, Greenland will be gone, and a good chunk of Antarctica will be gone, and sea level will be at least 10 meters higher, and those islands will be gone. So you can do all the conservation work you want on those ecosystems, and I can tell you they're all going to be extinct. Now, this mode of thinking, let's say, is not particularly lighthearted. Conservation biologists that I've talked to about this most of them haven't loved this. They're in desperate battles. The field of conservation biology focuses on saving species, and they're very focused on species. And frankly, they're looking at species going extinct now, and they're looking at land use changes and people cutting down forest now. And so it's very hard for them to say, I'm trying to protect this forest, but it's going to die anyway. But I actually think that's important. Think of ANWR. ANWR is arguably the sacred cow of the U.S. environmental movement, the Alaskan National Wildlife Reserve. Most of the organisms in ANWR are walking extinction. The climate of Alaska over the next several thousand years is going to be so completely transformed. I can't tell you what species of animals will live there, but I can tell you it's unlikely to be Arctic foxes. It's unlikely to be polar bears. Anything adapted to white conditions, not going to do very well. So we're talking about a huge ecosystem change here. And you can look at it in this negative way, but I actually think there's actually an interesting opportunity for scholarship here. Let's take conservation biology seriously. And what I mean by that is, if you compare the Earth, if you think about the Earth the way we think about the Permo-Triassic, the way Doug Irwin thinks about the Permo-Triassic, where we lost 90% of species. Now, my own view is that climate change is already causing a mass extinction, and coupled with human land use is going to cause one hell of a big mass extinction. It's probably not going to be as big as the Permo-Triassic, although it's too early to say. But it's going to be big. So let's ask the question now, Let's take this seriously. Suppose we were trying to save as much of the tree of life as possible. The tree of life is going through a bottleneck. That bottleneck is going to last roughly 100,000 years. The Earth will recover in about 100,000 years. And to me, just in terms of thinking about the problem, if you lose a species of lizard here or there, given what's going to happen to the whole tree of life, that may not be such a big deal. Losing all lizards would be a problem. Right? And so one of the questions or approaches, if you take conservation biology seriously, is you can ask, what kind of interventions are there to preserve as much of the tree of life as possible? Of course, some of those interventions might be considered completely unethical. And I'm not saying you should necessarily do these interventions. They often involve moving species. And once you do that, you're playing with a complex system that you can't predict. So you might make a lot of mistakes. So this is not something trivial at all. I'm just saying, if we step back and take climate change seriously and recognize the time scale of climate change, then there's an interesting problem here dealing with conservation that hasn't really been tackled by that community. And the kind of thinking here about networks and systems and robustness and resilience is exactly the kind of thinking that's needed. It's really more of an evolutionary approach and not a conservation approach in the way conservation biology is practiced now. Okay, so that was actually the end of my talk. I'd be happy to, I know a lot of people have thoughts and questions about this, all aspects of this interesting problem of climate change and resilience. So I'd be happy to turn it open for discussion now. Thanks very much.
We have a few moments for questions. David Hines, microphone, please.
Dan, that was a terrific talk, and it's a talk that not just the people in this room, but everybody in the country or indeed globally needs to hear, because you started off emphasizing that what is happening now is quite special and there is a reason for it, and it's not a subject for debate. One, what you didn't do, and which I hope you will do in future talks, is emphasize the role that education has to play in bringing about the change in the political landscape that makes it possible to think about local solutions. Because this is the hardest level in a way to hit. You could imagine, thanks to PCAST, that President Obama, who we hope will continue, understands all of this and can think, working with you, about federal solutions. But as you pointed out, that's not where the action has to be. It's got to be at a local level, and PCAST, I think, can only help if it comes up with innovative educational schemes that enable you to get to citizens, students, high school students, graduates, colleges, communities at the local level.
Thank you for that. I think that's exactly right. And I can tell you that many of our colleagues on PCAST share your concern and focus about education generally and STEM education in particular. And on climate education, I think there's been some progress, but I think there's a long way to go. And right now, Chris and I are working on a report for the president on should he be reelected next week. Should he want to prioritize climate change in his second term? And I think Bloomberg's endorsement is an interesting encouragement towards that. What are the policy options that he might have? It's very interesting when you ask people, you ask different policy experts, climate experts about this, they say, carbon tax, cap and trade, carbon tax. You say, okay, that's great. That turns out to require congressional action. What else do you think the president should do? Because frankly, if we go to the president and say, we think you should put a price on carbon, he's going to say, you think nobody's told me this before? The president's a very smart guy. So what we're actually looking for is things that we can recommend that are, frankly, politically attractive to him, that are doable, and impactful. And so we're working on coming up with a list of those, but education and, frankly, just showing general leadership and interest in this issue is a very important step. I hope that people will respond if the president shows continued engagement on this issue.
Other questions for Dan, please? Chris.
Dylan Farmer came back from a meeting he attended, I forget where he said that people were looking at some of the simpler, more naive sorts of geoengineering one could do. These would not actually deal with the carbon dioxide in the air, so they would not prevent ocean acidification from taking the marine food web, but they might deal with temperature and perhaps with sea level. And he said the frightening thing about them is that they're pretty cheap, and that a rogue actor could, put a bunch of aerosol into the upper atmosphere and so on. So, I don't know. I mean, the one thing that you didn't deal with in your talk, which I think is fine because you dealt with a lot of other excellent things, is the whole field of geoengineering and how fraught that is, and different classes of geoengineering solutions that people have talked about. But it seems as if we actually start looking at 7-meter sea level rises, people are going to look at all sorts of crazy things, not just seawalls and buildings.
I think that's right. I actually am one of those people who's among the group talking about geoengineering and have been for quite a while. For people who aren't familiar with what...
When I say crazy, I don't mean to say that...
No, crazy is a great explanation of it. No, you're not offending me at all. I think it's appropriate to regard it with some healthy skepticism because, frankly, it's terrifying. We're talking about an engineering system to change the climate of, or stabilize the climate of the entire Earth system. We know very little about it, actually. The idea is based on what happens when a big volcano erupts. So this is a picture of Pinatubo. Pinatubo put a lot of sulfur dioxide into the upper atmosphere, which gets oxidized to sulfate and then reflects light back to space. And so it reflects light. Now, one very important thing is that, and Pinatubo cooled the climate for about a year. And other big volcanic eruptions have done the same. To make this clear, reflecting sunlight is not the same as reducing greenhouse gases. Greenhouse gases work 24 hours a day, whereas aerosols only work when the sun is shining. So it affects things like the diurnal cycle, the seasonal cycle, because it's not the same. What's remarkable is actually how well it does work. That is, on the annual average, it seems to compensate for greenhouse gas warming remarkably well. And I'll show you that in a minute. Well, here, I'll show it to you right now. Here's just a simple calculation, and this is just a climate model. And I'll criticize it in a second, but let me show you first how well it works. This is a simulation with doubled CO2. So you can see this is the temperature rise in the world from a doubled CO2 experiment. And then this is the same thing with doubled CO2, but they turn the sun down 1.84%. So they're not putting aerosols in the atmosphere, they're just dialing down the solar luminosity in the model. Okay? And the net result is, you can see, it's not perfect, but it's pretty good. It takes away most of the change. Right? Now, this doesn't tell you what's going to happen to storms. It doesn't tell you what's going to happen to the monsoon. It doesn't tell you what's going to happen, all sorts of variability. So there's lots and lots of questions we don't understand. It turns out, if you ask me what the biggest obstacle right now is to this, it's actually its effect on stratospheric ozone. Right now, we don't know of a safe way to do this that's necessarily safe for stratospheric ozone. And that's a big problem. Because if we get rid of stratospheric ozone unintentionally, we could really cause ourselves a mess. About 5 years ago, at the American Academy of Sciences of Arts and Sciences in Cambridge, I held a workshop with about 50 people to talk about this issue of geoengineering at a time when it was still very new, and a lot of people, this was the first time they'd ever heard about it. Larry Summers was there. Kerry Manuel, we mentioned from MIT, was there. A lot of climate scientists who'd never talked about this before. And the idea was not that I don't necessarily embrace this, although I've got to tell you, it may be better than the alternative. But these are the sort of questions we asked. How do we do it? What does it do to the climate system? What might go wrong? Does it postpone the need to reduce emissions? And more importantly, and this is the biggest concern for most climate scientists, will it postpone the reduction of emissions because people think the problem is solved even when it isn't? One of the problems with this approach is that if you keep burning fossil fuels and fix it, so for example, if people have read the second Freakonomics book, those guys say, oh, this is cheap, do it. Literally, that's what they say. And I say, wait a second, you have no idea whether this works yet. You're talking about building an engineering system to support every living thing on the planet. And if you keep burning fossil fuels and you don't fix that problem, you need more and more and more of it. And so you get completely addicted to it. You can't turn it off. If you turned it off, this climate would crash. So it has to be a fail-proof system that through wars, through disruptions, continues to operate perfectly over timescales of thousands of years, or until you can figure out how to scrub all the CO2, pump it out of the atmosphere. So it's a daunting engineering challenge. Now, that being said, I like to call it a tourniquet sometimes. I think it's a little bit like what Winston Churchill called democracy. You know, it's the worst idea in the world except for the alternative, which is just letting climate change happen. And as you say, if the impacts get really bad and they're worse than we think, I mean, imagine if 2 or 3 storms like Sandy came up the coast every year. What would we do? I'm not saying that's going to happen, but imagine if that started to happen. We couldn't sustain that kind of damage on the East Coast every year. It would totally transform the way people live. And so at that point, the support for something like this might be substantial because, as you say, it is relatively cheap. Cheap relative to rebuilding the energy infrastructure for the entire world. Right?